go ahead. Well, good morning, AP Environmental students from Kentucky, and special good morning to teachers as well. We are continuing our series of online content review sessions. Today we are fortunate to have Debbie Wheeler from the Sayre School, who is also an AP Environmental Science reader, and Debbie will be reviewing energy flow and power this morning. I understand that there will be no calculator-based calculations required this year, but there will certainly be questions that refer to this, and this will hopefully prepare those of you who are listening for the exam. I'm Lou Akampora, and we've got colleagues here from Advanced Kentucky working to support you and in your coursework. We'll have quite a number of students participating, so please do turn off your microphones and your video, but do feel free to use the chat room. We'll be trying to engage you and hearing what you say. We'll be posting polls, and these polls are anonymous, so feel free to participate. No one's going to hold it against you if you're wrong, and sometimes misconceptions can be enlightening. This meeting and others are going to be archived at kyap2020.com. So you can look at the video, and there may be some support materials posted there. So once again, I'm going to turn this over to Debbie and let her take that away. So I will say good morning.
All right, I'm going to go ahead and start sharing my screen, and hopefully that's visible to everybody. Today we're going to talk about energy and energy conversions, and I'm also going to walk you through some experimental design, because we know that's going to be one of the questions, one of the two questions that you see on today's test, on the AP test this year. So just to start off with energy and ecosystems, where does the energy needed for living organisms originate? And please feel free to use the chat. Starting you off with a fairly easy question here. All right, so it's going to start with the sun. And then from the sun, we're going to start to enter our food chains. So you're going to need a little piece of paper here so you can start diagramming this with me. But this is a sample of a food web, and it has a variety of animals in it. Barn owls eat primarily small mammals that consume grain, insects, and earthworms. And you can see the direction of the arrows that we need to make sure we're using whenever we talk about food chains. If you would, take a moment to draw a trophic pyramid. And I'll let you get this on your paper before I take you back to that food chain. And then we're going to fill in the producers, the primary consumers, the secondary consumers, and the tertiary consumers, which will also be our top consumers. Okay, I'm going to take you back to that food web. Now, if you'll use your pyramid and go ahead and fill these in. So producers, primary consumers, secondary consumers, tertiary consumers. Make sure you're following those arrows carefully. All right, I'm going to go ahead and put my pyramid back up. Can you tell me who an example of a tertiary consumer would be? Love to see this appear in our chat room. Yeah, thanks, Stephanie. So that's going to be owls. What about our secondary consumers? Right? In that diagram, there were moles, shrews, birds, and owls. Owls could play both a tertiary and a secondary. What were some primary consumers in that diagram? And I see some people maybe didn't write down those. Primary consumers.
Maybe could you explain what makes something a secondary or a primary consumer?
Yeah, so our primary consumers are going to be eating producers. So I'm going to give away the answer to our producers. That should be the bottom part of your trophic level. So take a look at what's eating a primary, and that's going to be a secondary. And then tertiary is going to be anything that's eating a secondary. Yes, I see some good answers up there. So worms, insect, mice, and rats, as well as birds, are primary consumers. Moles, shrews, birds, and the owl. Notice birds can be both a primary and a secondary consumer here. And you're just always focusing on, what eats the producer, that's my primary, what eats my primary, that's my secondary, and what eats my secondary, that's my tertiary, okay? And we're gonna talk a little bit about why this is a pyramid in just a minute. All right, so let's use what we learned here. Can you tell me a primary consumer in this food web? Sorry, a primary producer in this food web. I see algae and seaweed. Awesome. Yeah, what about a tertiary? So algae and seaweed are primary producers. What is a tertiary consumer? What makes a consumer a tertiary consumer? What makes a consumer tertiary? They might be at the top. Usually we want to look and see, here's if the seaweed is my producer, and the seaweed is eaten by the sea snail, and the sea snail is eaten by the crab. So sea snail would be primary, crab would be secondary, and then the herring would be an example. Yes, I saw herring, gull, and common seal. So notice that here the seal can play a secondary consumer when it eats the fish, which is eating the seaweed. But if we look at the algae, limpet, lobster, and common seal route, we can see seals can be a tertiary consumer also. So there are two tertiary consumers, the common seal and the herring gull. All right, what are two organisms that are competing for the same food source? Two organisms that are competing for the same food source. Fish and sea snail, awesome. Those are both competing for seaweed. And I see limpet and sea urchin. Those are also good ones. Those guys are both competing for algae. So nice. So this was an FRQ from a previous, or one of the examples that was on our AP Classroom site. All right, let's make sure we know how to complete a food web. This was also a practice FRQ. So complete the diagram of this wetland food web by drawing arrows that show the direction of energy flow. On your paper, if you would write down these 4 squares: fish, algae, snail, and eagle, and then just do your best to connect those arrows. Okay, if you need another minute, please let me know in the chat box. All right, my first arrow, and I'll talk slow, Ty. Thanks for being here, by the way. Ty's one of my students. So I'm going to start with my producer. So can you type in what our producer is, where we need to start? Yep, algae, absolutely. See lots of algae. So I'm going to start to algae, and where should I go from there? What's going to eat the algae? Snail, definitely. One other organism will also eat algae. Fish, excellent. What's going to eat my fish? Awesome. Okay, so here's a sample of some connections we could make. So we've got algae being eaten by fish and snails. We have the fish being eaten by eagles. Eagles might also eat snails. And then some fish may be consumed by the snail, although maybe we're talking fish eggs at that point, okay? In this FRQ, you needed to have at least 3 arrows, and you needed to make sure your arrows are going in the same direction for credit. So that's one of the biggest things I see when students are drawing these food chains. They understand connections, but they may not put the direction of energy flow in there. Okay. See some interesting responses on there. All right. Here is another example of a question that we might see. It's worded as a multiple choice, but it asks us to analyze some data, and that's a pretty important skill. Take a minute to look at the table here at the top. The X in the cell indicates the organism is eaten by the consumer in the first column. And we're going to do this as a poll. So based on the data table, if the number of snakes were to suddenly decrease, which of the following changes would most likely occur in the food web of this ecosystem? So look carefully at that table. Remember, an X indicates the organism is eaten by the consumer in the first column. So we're choosing between A, B, and B, C, and D.
And we've got about half the people voting, so or polling, so we'll give them a few more seconds.
Okay.
It's too bad they don't let me vote or poll. I think I've got a good guess on this one. I'll give you 5 seconds and we'll let Debbie get on with it. 3, 2, 1.
All right. So A was the most common answer given on our poll, and that is correct. If snakes were suddenly to decrease, it would cause an increase in the number of shrews, and that's because shrews are eaten by snakes, as we can see from that X there. It would also cause a decrease in the number of hawks because snakes are an important food source for the hawks, as are the shrews. So nicely done. Okay, let's talk a little bit about some vocabulary terms associated with energy and energy flow, and that's gross primary productivity and net primary productivity. And I think it's really easy to think about these. You know, if you've ever gotten a paycheck, an official paycheck from a business, gross is sort of what you expect to make when you add up what your hourly wage is and multiply that by the number of hours you work. And then you have taxes taken out. So net is what your check is actually going to be written for. That would be the net primary productivity. So in this example, there's a lot of good information here. For example, 1% of solar energy striking producers is captured by photosynthesis. And so that's kind of an amazing statistic, I think. 99% passes through producers and does not get used in photosynthesis. So That photosynthetic percentage is our gross primary productivity, GPP. Now, plants don't just store all of that sugar that they make during photosynthesis. They're going to use some of it. So this 60% loss to respiration, that's what they're using. And then the net is going to get stored and potentially passed on. So that equation up here, GPP minus R equals NPP, that's the gross primary productivity minus respiration equals your net. And hopefully you've written this down, because I'm going to ask you to use that information in just a little bit. Okay. Please let me know if I need to slow down, or if you need a minute to write a few things down. I don't want to go too fast, but I also don't want to go too slow. All right, so based on that last slide we just reviewed, describe the process of primary productivity. And feel free to type this in the chat. Describe the process of primary productivity. You can be brief. Doesn't have to be accurate, because we're not taking the test yet. There's a certain amount of energy that each level gets. That's what some of the answers I'm seeing. 100% of the energy starts out, then 10% gets transferred to the next level. Ooh, we are going to get to that. We're going to talk about energy transfer in just a minute. Thanks for that chemistry input. Okay, oops. Have some writing on the screen. It's got to be a Sarah student. We may have to erase that a little bit. Thank you. So the rate at which solar energy is converted into organic compounds, which are sugars over time, is a good way to describe primary productivity. In a multiple choice question, here's some options. And if you'll start a quick poll for us, Lou, that'd be great. All right, so in this question, which of the following best describes gross primary productivity in an ecosystem? Is it A, it's the total amount of energy captured by producers plus the energy used by consumers? Is it the total amount of energy captured by consumers? Captured by producers minus the energy that producers respire? Is it the total amount of energy lost as heat during energy transfer between trophic levels? Or is it the total amount of solar energy captured by producers through photosynthesis over time? Which one of those best matches the definition for gross primary productivity we just discussed?
And just remember, you can move that poll box out of the way so you can read the questions, those of you out there.
Yes, thank you for that tip. That's what I was doing too. Moving it over so I could read the whole thing.
We've got about 50% voting, so don't be shy. I'll keep this open for about 5 more seconds. And again, this is anonymous, so don't worry about it. You're not going to be graded on this. 3, 2, 1.
All right, so it looks like we have most people choosing D, just barely. D is the best answer. Gross primary productivity is the total amount of solar energy captured by producers through photosynthesis over time. B would be a better answer if we were looking for net primary productivity, because that's the amount of energy captured by producers minus what they respire. Okay, speaking of net primary productivity, let's do another poll. Which is the best definition for net primary productivity? So is it A, the amount of energy captured by producers through photosynthesis over time? Is it B, net primary productivity is the amount of energy lost by producers through respiration over time? Is it C, the amount of energy lost through respiration by producers subtracted from the gross primary productivity of an ecosystem? Or is it D, the amount of energy lost through respiration by producers added to the gross primary productivity of an ecosystem? All right, we got about almost half. Keep voting.
Teachers are allowed to vote too, and you don't have to vote with the right answer.
That's right. I can't tell who is answering what from my end, so.
Okay, that's almost a minute, so we'll close it in 3, 2, 1. That's good.
Okay. So the best answer here, and I just realized I think my my next slide is incorrect, so I'm going to leave it on this one. So the best answer is C, net primary productivity is the amount of energy lost through respirations by producers subtracted from the gross primary productivity. Okay. Here's a calculation problem. You aren't going to have calculations on this exam, but this is a fairly simple one. Might not even really require a calculator, but let's give it a go. The net primary production of a pine lava forest on a lava flow on Mount Fuji is about 175,000 kilocalories per meter squared per year, and plant respiration is estimated to be about 115,000 kilocalories per meter squared per year. What is the total amount of energy transferred during photosynthesis for this ecosystem? So think about that equation that we had up. Go ahead and do some relatively simple math and see if you can come up with a good answer. All right, getting close to half. Keep voting. Remember that GPP is the net plus the respiration if we're using that in reverse.
And that's about a minute, so we'll end the polling here.
Okay, and hopefully, looks like we may have had a little bit of misunderstanding. So you're adding those two numbers. You're adding the primary production and the plant respiration, and that will give you the gross, which is 290,000 kilocalories per meter squared per year. Okay, so just knowing that equation will help us answer those. All right. Here's another polling question for you. Of the following ecosystems, which has the lowest net primary productivity measured as kilocalories of energy produced per square meter per year? So this is asking you to go over a little bit of what you know about biomes, and which do you think has the lowest primary productivity, and make sure you pay attention to the units measured as kilocalories of energy produced per square meter per year.
And I can't believe I'm saying this as a chemistry teacher, Debbie, but would you, after we go over this, explain why the units are so important and what they measure?
Absolutely, absolutely. All right, got a little over half. So is it taiga, is it open ocean, temperate grassland, or estuaries?
I don't know, and I wish I could vote on this one, but I don't have the option to vote. So that's 1 minute. I'm going to close the polling in 3, 2, 1. No.
Okay. Just to make sure we know, what is an estuary, by the way? What's another word for an estuary? And hopefully, I'm not seeing my chat box come up, but Yeah, okay. I'm seeing a few options here. An estuary is also known as a delta, and it's going to be where a river enters the open ocean. So the best answer is open ocean, and that's because the units are in kilocalories of energy per square meter. So the ocean has really high productivity, but if you're dividing that over the area, 70% of our globe is ocean, it's going to cause the number that you get to be fairly low. So this is a tricky question, I think, and it's one of the reasons why I wanted to go over it with you, so you could think about the fact that open ocean does have very high productivity for the planet, but if you divide it by square meter, it ends up being the lowest net primary productivity. Any questions about that, or anything that sounds confusing about it? Okay. Most of you answered B, so that's good. That's awesome. All right. Let's take a look at energy transfer next as we go from trophic level to trophic level. So what percent of energy is transferred from one trophic level to the next in an energy pyramid? Yeah, and I saw some of those. I saw 10% listed earlier, so that's awesome. That's absolutely right. 10% of the energy is transferred from one trophic level to the next. So, for example, if producers contribute 100,000 calories, how many calories would be available to herbivores? Remember, herbivores are our primary consumers. Yep, you're right, Ty. 10,000 calories would be available. What are herbivores using those calories for? Because we know that 10% is going to be reduced as we go from primary to secondary. So yeah, for finding food, good, for heat, for moving around. So at every trophic level, you don't get all of the energy that's available there transferred, only 10% gets transferred up. Okay, so let's practice a little bit. Assume an owl needs 400 calories to meet its basic daily needs. Complete this energy pyramid showing the available calories at the other trophic levels. So if you'll draw this energy pyramid, we'll go backwards, and you can use your chat to fill in answers. It's always interesting keeping an eye on the chat, seeing what's going on over there. All right, so can you tell me, this is our owl up here. What level is just below that? Secondary, nice. So there should be 4,000 calories, that's correct. And then below that, below secondary, primary consumer, how many calories? 40,000, excellent. So below our primary, what level is that? What's the base of our energy pyramid? Producers or autotrophs. Oh, nice vocabulary words. Yeah, so there should be 400,000 calories available. So that's some fairly simple, energy pyramid completion we should be able to do. Practice just a little bit more. Algae in an aquatic food chain convert solar energy into 93,000 kilocalories of plant tissue. Which of the following values best represents the amount of energy available for primary consumers in the food chain? Oops. Yeah, I'll go ahead and go past that one since I already hit it. Yeah, so it's 9,300. Let's do one more, and I'll try not to hit the advance button on this one, and maybe we can run a quick poll and make sure everybody's good on it. In a given ecosystem, producers convert solar energy into 15,000 kilocalories of chemical energy. Which of the following is the most likely amount of energy available to secondary consumers? So make sure I bolded it, make sure you're reading, which level consumer it is. You're thinking about those questions carefully. All right, I got a lot of fast answers coming in. This is good. This is Seems like we feel pretty confident about this content. Okay, keep them coming. Almost at 100%.
And we're coming up on a minute, so I'll stop this in 3, 2, 1.
Awesome. All right, B is the right answer. That was the majority of the folks that answered, so I think we're pretty good with this information. That's excellent. Okay, which of the following best describes the movement of energy in an ecosystem? So when we talk about energy flow, I really want to make sure we differentiate between energy flow and matter, the flow of matter. So let's talk about energy in this question, then we'll discuss the flow of matter. So is it true that energy is constantly recycled by decomposers for use by producers? That would be A. Is it B? Energy is harnessed by producers and available energy decreases with each trophic level transfer. Is it C? Energy is absorbed by plants through water and soil and then moves up the food chain through consumers? Or is it D, energy is magnified as it moves up the trophic levels and tertiary consumers store the most energy in a food web? All right, answers are coming in fast and furious. I like it. If you've answered the poll, go ahead and answer this in chat. What is the difference between the way energy moves in an ecosystem and the way matter moves in an ecosystem? I'll say that again. If you've answered the poll question, go ahead and answer this question. The difference between the way energy moves and the way matter moves.
And I'll close the poll in about 5 seconds. 4, 3, 2, 1.
Okay, so most folks answered B, which is the correct answer. Energy is harnessed by producers and then it decreases with each trophic transfer. Energy does not get recycled, right? I saw Sally's correcting that. Yeah. So energy does not get recycled. Matter does. And when we talk about matter, we're talking about nitrogen, carbon, all of those sorts of sulfur, all those biogeochemical cycles that we need to know for this content. So that material recycles, energy does not. It's not uncommon for folks to tell me that, the soil is providing energy for producers. The soil provides nitrogen for producers, but it's not providing energy. So we want to make sure we know the difference. Okay. Now let's put some of this knowledge to work. Explain why it takes many hectares of wetland to support a pair of eagles. And let's answer that in chat. So please begin. Why does it take many hectares of wetland to support a pair of eagles? Energy is transferred. But it gets less powerful, not necessarily less powerful. It's just there's that loss as we go up. Yes, energy decreases as we go up in trophic level. And where are eagles in our trophic pyramid? Yeah, they're going to be at the top. And so, like Mr. McCann said, land is needed for all levels of an ecosystem. So let's look at what the correct answer was on this section of an FRQ. To support a pair of eagles, there must be a large amount of biomass. Less energy is available at each successive trophic level because of that 10% rule. Some energy is going to be lost as it moves up. Some is going to be transformed into a less usable form. We're going to talk about the second law of thermodynamics in a minute. Hopefully you guys are pretty familiar with that. And then some biomass is always not digestible, so it doesn't necessarily go to the next level. So you might think about plants are producers at the bottom of the food chain. They have this root system that's probably not going to be consumed by herbivores. And so that is biomass that will not be transferred up. Okay. Yes, Lou, I love the second law too. It's pretty cool. All right. It is very possible on May 18th, when you take this exam, they're going to ask you to look at a diagram and interpret a diagram. So please take a minute to look at this one. It's titled Relative Solar Energy Amounts over 2 locations over a year. And there is a multiple choice question associated with this. I always like to look at the diagram and think about what it tells me before I look at the question it's going to ask me. Sometimes that's just a way for me to get that information clear in my head. So assuming all other variables are constant, which of the following is the most likely conclusion about the greatest potential for gross primary productivity that can be supported by this data? Okay, so take a look at location 1 and location 2, what they've got in common, how they're different. And then let's answer our poll. Gross primary productivity is the same for both locations all year. That's choice A. Choice B, gross primary productivity in location 2 is greater than in location 1 in December. Gross primary productivity 2 in location 1 is greater than in location 2 in March. So that's choice C. And then choice D, gross primary productivity in location 2 is greater than in location 1 in September. So it's asking us to look at specific months and then just interpret which of those statements is true. Okay, polls are coming in. Please answer if you haven't already. Got close to half now, keep going. All right, almost done.
That's about a minute, so I'll say
There you
3, 2, 1, and
okay, most folks answered C, and C is correct. Gross primary productivity in location 1 is greater than in location 2, specifically in March. All right, let's talk about those laws. And let's do the first one. In the chat room, if you would, what is the first law of thermodynamics? One of the things I love about AP Environmental is it's got physics, it's got chemistry, it's got some social science, some biology, obviously. It's got a lot of content. So what is the first? Energy cannot be created nor destroyed. Yes. So it can be transformed from one form to another, but it cannot be created nor destroyed. That also means that energy in a closed system remains constant. Okay. So those are important concepts for us to think about. Let's apply those in just a minute. I want to talk about a perpetual motion machine. So can I, and I wish I had, you know, if I were in the classroom, I'd have my generator out and show you, hey, can I spin this turbine, get my generator going, and then instead of lighting a light bulb, just have it run itself. And I'm seeing some no's, not really possible. And that's because of the second law. What is the second law of thermodynamics? Energy goes to entropy. I like it. Can I have a little more from somebody else? Okay, we'll write this down then. So the second law of thermodynamics states when energy is transferred or changed from one form to another, there's always going to be less energy available at the end of the transfer than at the beginning. Okay, always going to be less energy available. And we say that that energy is lost. It's not really lost, but just changed to an unusable form like heat. Okay, so entropy is less ordered systems or chaos. And I always like to use the example of, you know, you get ready for the school week on a Sunday and clean up your room knowing that things are going to get chaotic and, you know, you want to be ready for the week. And that's what happens over the course of the week. Without an input of energy, it gets more chaotic. You have more entropy or less order happening. Okay, so let's apply these two laws to a question we can get polled on. Which of the following best describes the first law of thermodynamics? Is it A, energy always changes from a more useful, more concentrated form to a less useful, less concentrated form? Is it B, in a closed system of constant mass, the energy involved in any physical or chemical change is neither created nor destroyed, but merely changed from one form to another? Is it C, heat always flows from a hot body to a cold body? Is it D, entropy of a system increases as the state of disorganization in the system increases? Or is it E, in a reversible process, the entropy of a system is constant, whereas in an irreversible process, the entropy of the system increases? And thank you, there's our poll. So A, B, C, D, I did have E in this one. All right, we're already at 50%. That's awesome. Okay, a few more people left to vote. A, B, C, D, or E.
And we'll keep it open for about 5 more seconds, please. So if you've got a answer, please go ahead and put it in 3, 2.
All right. So most folks answered B, which is great news. That is the answer. That neither created nor destroyed always sticks in our head. So it's nice when that's part of the question that gets asked. Okay. Here is another question for you. If you can relaunch our poll, Lou. Losses of usable energy between successive trophic levels in an ecosystem are best described by which of the following? So now we're going to apply this to our biology. Losses of usable energy between successive trophic levels in an ecosystem are best accounted by which of the following? The first law of thermodynamics, the second law, C is the law of conservation of matter, and D is the process of ecological succession. So those are all terms we should know the definition of. All right, we're already over 50%. Nice. Keep them coming in. All right, take a few more seconds here. We're at 66%. That's good.
That seems to be most of the respondents. So I'll close the polling now in 3, 2, 1.
Okay, and most of you answered B, which is the correct answer, the second law of thermodynamics. Okay, I have another poll for you here. The maximum efficiency possible in an energy conversion process that is not limited by the second law of thermodynamics, okay, not limited by the second law, is going to be what? A, 100%, B, 95%, C, 30%, D, 15%, or E, 1%.
And I don't think we're going to need a minute to answer this one, so I'll wait till we've had most of our respondents come in.
Sounds good.
And our responses are tapering off, so I'll say 3 more seconds. Okay.
All right, and most of us did answer A, 100%. So the second law of thermodynamics is one of the reasons we have limits there. Okay, I'm going to quickly go through states of energy just so that you know those, because I do want to get to experimental design towards the end, so I'll move through this fairly quickly. If somebody on chat could tell me the difference between potential and kinetic, that'd be great. Or I can just throw it up there for you. So potential is stored energy. Kinetic, yeah, movement, energy in motion. We can group these forms of energy as kinetic or potential. If you'll take a quick moment to think about which is which, and I'm going to throw answers up for you in a minute. So all of these can be grouped as either potential or kinetic. Yeah, keep in mind kinetic is moving, potential is stored. Okay, so I've grouped these. Kinetic is radiant, sound, thermal, electrical, and mechanical. Potential, another group I had, is chemical, nuclear, or gravitational. So if you will quickly in chat, tell me if it's potential or kinetic, and then which one of those specific types. And if you can't remember, that's okay. I will share that with you. Like I said, I want to make sure we have a little bit of time. Potential chemical, excellent. Charcoal briquettes, those are what you use if you're grilling out and you don't have gas, propane outside. This is also going to be potential chemical. Nice. So water behind a dam, and it's going to flow through that dam and eventually turn the turbine. But what is the water behind the dam called? Potential. Gravitational. I think that was the abbreviation you're going for there, Sally. That's good. A baseball being thrown. Yep. Potential is, or sorry, kinetic is the best answer. And then kinetic mechanical. You may not remember that whole list. And this form of energy. So is it kinetic or potential? Yes, it is kinetic. And you could say thermal. You might also say light or heat. Nice, good. I see those appearing in chat pretty quickly. Uranium-235. So this is the material that's going to be used in nuclear power plants. It is potential, and it's potential nuclear. I sort of gave that one away. When it's releasing heat, we would call it kinetic thermal. So an operating wind turbine, and it's moving. Yeah, that's our tip. It's moving. So it would be kinetic. And this is where we can think about transfer, because the way I'd see you using this information is you've got kinetic energy that's transferred to mechanical. And then good, I see mechanical putting up there. And then the mechanical is eventually going to be electrical. Okay. And each time we have one of those happening, we will, have a loss of energy efficiency. Okay, and I'm going to go through these fairly quickly. I won't bother with a poll if you guys want to just type in an answer. An energy transformation occurs and results in increased disorder. What would you call that? A, heat flow, B, kinetic, C, potential, D, the first law, or E, the second law? I'm seeing lots of E's. I like it. Yes, second law of thermodynamics. Here's another question for you. The efficiency of the conversion of light energy to chemical energy in photosynthesis. Kind of a review from an earlier slide. Is it A, B, C, D, or E? I'm seeing lots of E's. It is E. Remember, only 1% gets transferred. Awesome. I wanted to throw in a couple of other pieces of information that you might see on the exam. Electricity is considered a secondary energy source. A primary energy source is used to generate the electricity. Can you type in the chat room some examples of sources used to generate electricity? Coal, yep, exactly. Wind, like that wind turbine we just saw. Excellent. Fracking would be how we get natural gas. You could burn natural gas in a turbine to create electricity. So awesome. This is a good thing to know if they ask you a question about electric cars. Electric cars are really running on a secondary energy source. And when you're looking at the impact of an electric car, you have to think about what the primary source is that's running that car. Okay, awesome. Very good answers. Again, let's do this on chat just for speed and efficiency. If an incandescent light bulb used for lighting has an efficiency rating of 5%, then for every 1 joule of electrical energy consumed by the bulb, which of the following is produced? Okay, efficiency, you're not going to be using a calculator, but this is one you can probably do without a calculator. So if an incandescent bulb is 5% efficient, nice. So I see either C or D in there. Yeah, the best answer is D. So for every 1 joule of electrical energy consumed, it's only producing 0.05 joules of light. So it's producing 0.95 joules of heat energy, which is one of the reasons why we think of them as being very inefficient bulbs. Okay, let's get into talking about experimental design. So I'm going to read this paragraph. Feel free to read along with me. And then I want you on your paper that you hopefully have with you just to diagram the relationships in a food web that you might see. So oak trees produce large autumnal acorn crops every 2 to 5 years and produce few or no acorns during intervening years. Acorns are critical food for white-footed mice. It's going to be a huge part of our food chain. Mice are important predators of the pupal stage of the gypsy moth. This introduced insect periodically undergoes outbreaks that defoliate millions of hectares of oak trees, decrease tree growth, survival, and acorn crop production. As an abundance of acorn provides foods for white-tailed deer, mice and deer are the primary host for the black-legged tick, which carries Lyme disease. So take a minute to diagram this food web. And you should have in your food web the acorn or the oak tree really specifically, the deer, the mouse, the gypsy moth, and the black-legged tick. Okay. So I'm going to go ahead and show you this so that I can ask you a little bit about design. Your diagram should look like this. Remember that your arrows should go in the direction of energy flow. So we have our oak tree producer down here. We have gypsy moths, white-footed mice, white-tailed deer are our primary consumers. And then white-tailed deer and white-footed mice are also going to be consumed by the black-legged tick. It's a secondary consumer. One thing just to point out is, you don't assume that the smallest organism is going to be lower on your food chain, your food web, or your energy pyramid. You got to look at what eats what. So for primary consumers are eating producers, secondary consumers are eating, and not completely eating, but feeding off of primary consumers. Where does a parasite fall? I mean, you could call it a parasite, but we're just looking at the direction of energy flow. And so in this case, we're going to put it and call it a secondary consumer because it is eating or feeding off of primary consumers, Sally. Okay, just so you know how the points broke out for this, you get 2 points for putting all 5 components in and showing the proper connections. You get another point for placing the arrows in the correct direction. And we didn't label, this one does not show labeled food webs, so it's only going to get 3 points instead of a possible 4. Let's see how we can use the same information to do an experiment, to create an experimental design. Okay, so design an experiment to test the relationship between acorn production and gypsy moth population. And we need a hypothesis. And what I really want to see is, can you identify the independent variable and the dependent variable? That's pretty critical for your hypothesis. And then we'll talk a little bit about how we could design an experiment. So, so take a minute to think about it. I've got the information both from the food web that the sample food web we saw, as well as that paragraph up on your screen. Think about a good hypothesis and what your independent variable and dependent variable might be. All right, I see independent variable is acorns, dependent variable population of moths. Okay, how could you put that into a hypothesis? It doesn't have to be Solly, could be anybody. If our independent variable were acorns, and maybe we could be more specific amount of acorns, that'd probably be good. And our dependent variable, we think it would affect the population of moths. Any other folks want to try this before we take a look at some optional answers? I'm looking in the chat to see if we've got some. More acorns produced, population of, or more moths produced, population of acorns increases. More acorns, more moths. Nice. Okay, let's look at some optional solutions to this. So whenever you're creating a hypothesis, I've got in red here, the direction of change has to be specified for both organisms. The samples we've got up there do that, which is pretty awesome. So it's really important that you just don't say, I think if the moths change, then the acorn number will change. You have to show directions for both of those. And if you say change in acorns is going to cause a change in moths, you need to make sure that you explain it's through the connection with mice. And I'm going to go back. So when there are more mice, they're eating the pupae of the gypsy moths, and that's what's going to cause a change in the moth population. Okay, I'm going to go to one of the other, actually, let me go to hypothesis real quick. So your hypothesis samples could have said, if the number of gypsy moths increase, then the number of acorns will decrease. And specifically, that's due to defoliation and stress on the oak trees. You could have said, if there's a decrease in gypsy moths, there will be an increase in acorns. You may have said an increase in acorns will lead to increased mouse populations, and that decreases the moth population. Or if acorns increase, then the mice will preferentially eat acorns, and that will cause an increase in gypsy moths since they're not going to be feeding on them. So again, just important that you have a direction both for your independent variable and your dependent variable. I don't see null hypotheses written very often, but it is possible you say there is no impact. So you can have multiple statements that discuss no impact on acorns and gypsy moths. All right, Lou, do we have time for one more?
I think we got about that time for one more, Debbie. We're right at about 3 minutes before the hour.
Okay, I'm going to skip over the remaining parts of this question because I want to give you a new one. So an ecologist is interested in the effect that fire intensity has on the biodiversity of tree species. Describe the control group for an experiment that examines the effect of fire intensity on the biodiversity of tree species. You will need to know the independent and the dependent variable here in order to come up with a control. So if you would take a minute to come up with a good independent variable and dependent variable, and then a control for this experiment. And just type that up in the chat room. It's okay to be wrong. I just appreciate, seeing what you're thinking. Independent variable fire intensity, dependent variable types of trees. And maybe we want to expand on types of trees just a little bit. As we want to talk about biodiversity, but yeah, those are good. What would be a good control? Yeah, number of different species of trees. I like Sally. Control no fires. All right, let's see how we did. So control group would be an unburned area that has no fire intensity, and that's our baseline for the amount of biodiversity. Awesome. All right, I should probably end there. Make sure that you practice with designing an experiment, because we definitely know that's going to be one of the questions that you're going to have on May 18th. And hopefully this session was helpful as you reviewed energy and energy flow and ecosystems.
And thank you so much, Debbie. That was terrific, Ms. Wheeler. And this session will be archived on KYAP 2020. So thank you all those participated. Excellent job, students and teachers. And I will sign off and say have a good rest of the day, and hopefully see most of you next week. Bye-bye now.